All right, we're going to talk about temperature this week. So I wanted to start out with looking at some relatively current temperatures. Uh, a lot of things influence temperature, but one of the biggest is air mass motions. Air masses are divided by fronts. We talked about that some. We're going to get a lot more into that. So we had here, this was early on Sunday morning. At that time, we had a cold front, basically stretching from a low that was kind of over parts of West Virginia and south down along the eastern seaboard. To the west of that low, continental polar air, cold air. East of that low, maritime tropical air. And up to the northeast of the low, it would have been maritime polar air. So we have a couple different air masses coming together here. And if you look at that, what does that mean? Well, it means we have winds that are coming around that low pressure system. They're rotating counterclockwise, as we've discussed. With that, you have northwest winds on the west side of that low. Think about it. Northwest takes you up into Canada. So you're pulling in Canadian air with that northwest flow. To the east of that low, we have northeast or east winds. Where's that air coming off of? The North Atlantic. North Atlantic is fairly moist, but it's also relatively cool. So we have a maritime polar air mass. Now, along the southeast coast of the United States, we have the Gulf Stream. So when you look at the Gulf Stream, what do you get? You have warm water out there. Temperatures are in the 70s, almost 80 out there over the water because the water temperature is that. And this air comes up along the east coast of the United States many times in the winter, and you wind up with extreme temperature contrast. You bring in the polar air, continental polar air coming in from Canada, and along the east coast you have maritime tropical air coming in from the Gulf Stream. So what you wind up with is temperatures in the 60s over the Outer Banks, and back over Ohio, West Virginia, the Midwest, temperatures are in the 30s. So when a front goes through an area, that pulls in that much colder air. By the same token, if a warm front passes through your area, it pulls in much warmer air. So one of the biggest influences on temperature are fronts. They pull in advection. The tighter the temperature gradient is, in other words, if you were to go along, we'll take an example of go from Charleston, West Virginia to Louisville, Kentucky. And if the temperature dropped 40 degrees over that distance, that would be the temperature gradient. And how many degrees it drops, how quickly it drops, is an indication of how strong that temperature gradient is. If the temperature only went down 2 degrees in that distance, it's a pretty weak gradient. If the temperature goes down 60 degrees in that gradient, it's a pretty strong gradient. So with this is yesterday. I wanted you to take a look and see Charleston's Yeager Airport. This is what we call a meteogram. What is a meteogram, right? It's an XY plot. We do a lot of that in here in meteorology. We're plotting every hour or every minute's temperature on a graph with time. And that's all we're done. We're just taking one location, in this case, Charleston, West Virginia, and we're plotting the temperature with time. And here you can even see that says temperature right there. So that's the collar. But we wanted to choose a couple extra things. We put in dew point, which is a measure of moisture, and relative humidity. So the closer the dew point and temperature are, the higher the relative humidity would be. So yesterday morning, about 6 a.m., something happened. This was 6:40 a.m. yesterday. Temperature is 51, dew point's 48. At 7:40, 1 hour later, the temperature is 46 and the dew point's 39. What happened? Well, what happened was that low we were looking at moved to the northeast of Charleston and the continental polar air mass arrived. Notice how the temperatures have been going down ever since. And overnight, last night, they went down into the mid-30s as well. The dew point got pretty close, so you see the relative humidity went up. So this is just an example of looking at temperatures real time using what we've learned about air masses a little bit here to see the influence and why we have a change in temperature. And that's one of the things I'm sure you're all interested in. Why was it so cold the other week and this week, relatively mild it's been? Uh, so let's look at a broader picture. What influences temperature? So if I were to go here, what are some of the causes of heat transfer? So first, let's define temperature. What is temperature? All molecules move to a certain extent. Some a lot more than others. So the faster they move, the more kinetic energy that molecule has. And they move in random motion. I always thought it would be interesting if they all moved in one direction to see what happened, but that's never going to happen, thank goodness. Otherwise, I don't know what would happen. It would be it would just be an impossibility. They also have potential energy, and the way you transfer energy between molecules is called heat. It's between two substances is brought together. So we've just talked about temperature gradients. The second law of thermodynamics says, hey, heat flows toward lower temperature. So that would mean that, oh man, now that cold air came in. Well, at the same time, all the heat was trying to flow from the warm air into that cold air. So right at the gradient, it actually might have been tightening up, right at the very front. And there are a lot of ways that heat can flow in the atmosphere. We talk about radiation. We talked about that all last week. Conduction. Think about this one. If you were to put your hand on a hot pavement in the summertime, your hand would kind of burn, wouldn't it? Well, what happened was the hot pavement transferred heat through conduction into your hand. That's all that is. Happens with pots and pans when you're cooking. You heat the stove, heat goes in through the pot and into the food that you're cooking. Conduction. Convection. Convection happens in fluids. Air is a fluid. We're going to talk about that. Latent heat. That's the change in water between a gaseous state, water vapor, a liquid state, like you see in raindrops, or a frozen state, like you see in snowflakes. The amount of heat required for that influences temperatures. So we've talked about radiation, microwaves, classic example of how radiation brings in heat into food, for example. Conduction. Certain things are way more conducive for heat transfer. Air is one of the least conductive. So, literally, conduction plays a very little role in heat transfer in the atmosphere, except near the immediate surface of the ground. So, with that in mind, conduction is not a big component of these things, but it's still there. Convection. All right. You ever look at water boiling? You see these little bubbles coming up through the water? That's convection. What it means is, right by the ground, the air is getting heated up. And it begins to rise as it got warmer. Eventually, it's cooling in the atmosphere because the atmosphere cools with height. Air is going to expand because the pressure is lower up there. And when that happens, it cools. Eventually, it gets cool enough, it comes back down. It literally makes a big circle. So all we have done is transport heat from the surface of the air, of the ground, up into the air, some height, and then back down to the ground again. So we're completing a loop where we're transporting heat upwards, bringing cooler air downwards. So that is convection. It happens on a small scale, like you see a cumulus cloud. It can happen on a much bigger scale. So sensible heating of the air. All that includes is conduction and convection. Doesn't have anything to do with moisture. Here we go. Latent heat. Latent heat is more difficult. All right. Think about it. If I am going to take a liquid and make it into a vapor, when you see the steam coming off when you're boiling water, you had to add heat to that water to get that steam, right? If you want to melt ice and make it water, you had to add heat to it. So anything going from a solid to a liquid to a gas, you're adding heat to that water. So that means a solid will have very little heat content. However, a gas will have a lot of heat content in it. And when the gas then evaporates, or condenses, excuse me, and becomes a liquid again, what happens is it releases that heat. So when it goes the other direction from vapor to a liquid, like you would see in a cloud, you have water vapor and then all of a sudden you see a cloud appearing. Guess what? Heat was released at that moment in time to make the liquid. So we've now added heat back into the atmosphere at that point. And then when it eventually freezes, when it gets high enough up in the atmosphere, we've added more heat to the atmosphere. So latent heat and water is the only substance in the atmosphere that changes state that can have latent heat. So if we're along a continent where latent heat is going to be maritime air, say I'm on the west coast of the United States, San Francisco, Los Angeles would be another example. Seattle is a great one. The temperature there does not change nearly as much because of the influence of the ocean. Ocean doesn't change. It takes a lot of sun energy to heat the ocean up. So with that, the ocean doesn't change much. So what do you wind up with? You wind up with temperatures maybe getting a little colder in winter, but not a lot, not getting as warm in summer. Now you go in the midsection of the country. Here's St. Louis. If I were to do Oklahoma City, or if I was to do Columbus, Ohio, you would see the same kind of curve because you're away from the middle of the oceans. If you're in the oceans, any island that is in the ocean, you're not going to see that extreme. That's what makes England kind of interesting because it is in the middle of an ocean. It has it around it, so it doesn't, and it's a cold ocean up there. So it doesn't get as cool in the winter maybe as it would, or as warm in the summer as it would. The ocean moderates its climate. Radiation, we talked a lot about that last week. You can see here, this is basically showing you the 100% solar radiation coming in and how all the complex things that happen to that little bit of radiation coming from the sun to impact the atmosphere, where it's absorbed, what's going on with it. We have both the shortwave and the long-wave radiation there. So, on the Earth's surface, we're going to transfer heat like to a cumulus cloud. All right, if I start with convection, I have pulled warm air from the ground up. Oh yeah, at some point, I am going to get water vapor transitioning to a liquid. Oh, that warmed the air even more. So it keeps going up. That's how your cumulus clouds build. They keep getting heat added to it from water vapor condensing into a liquid. Keeps making it warmer than the surrounding air because you notice there's air around it that's dry. There's not a cloud there. So that air will be cooler. There's also a surplus of solar energy that hits basically between the tropics of Capricorn and Cancer. They have a lot more solar energy down there. So the Earth hates the temperature to have a gradient. It would love everything to be uniform. And that's what it's always trying to do. That is why storm systems exist, air masses exist, ocean currents exist, to take all this heat energy that's down there around the equator and transport it north to the poles. How it does that is through these different mechanisms of storms. Hurricanes transport tremendous heat from the tropics up into the mid-latitudes. We're always trying to even out the temperatures throughout the world. It doesn't happen and never will, but we try with the atmosphere. So air masses, like we talked about, I showed you a classic example there in Charleston, West Virginia, of the temperature dropping as the cold front went through. It was only about 10-degree drop, but it was still a 10-degree drop in temperature, and the temperature stayed down. And that was a means of cold air coming in. And if you looked on the eastern side of it, what happened? Warm air was coming up from the south. So there's always an imbalance. Just because the sun doesn't heat uniformly across the earth, because we have oceans, we have land. All of that causes an imbalance and changes in temperature. So let's just look at a local budget. If I was at your house, sunny day. So in the morning, we know that infrared radiation is leaving. There is no solar radiation coming in. So what's happening? Well, the air temperature is going to drop because obviously I'm losing energy through infrared radiation. At some point, solar energy is going to begin to pick up. When that happens, and it reaches a point where there's more solar energy coming in than there is infrared radiation going out, the air temperature and the Earth's surface is going to begin to warm. So the temperature begins to rise. Noon may be the maximum amount of solar energy, but it continues going into the afternoon. So at some point in the mid-afternoon, the ground is heated up enough that the infrared radiation and the solar radiation, which is now diminishing, reach the same point. Same amount of energy is coming in as is going out. That's your maximum temperature. Now, in the evening, the ground is the hottest it's going to be when it's losing solar radiation very quickly right at sunset. So the temperature actually is going to fall pretty quickly and then slow down as the ground has cooled and the amount of infrared radiation is diminishing. Snow is a great example of why temperatures stay cold. Think about it. It has a very high albedo, so all that solar radiation is coming in and just getting bounced right back out into space. When you had snow cover the other week, temperature stayed a lot colder than if once the snow cover goes away. Bare ground will warm a lot faster. And this is just a heat island effect as well. So I hope you got a little bit out of this. Let me know if you have any questions.